How's it going, everyone? My name's Robert Shaw. I'm with Derek, Siper, and Raul, and we're going to be going through our final presentation for the ME 2110 class. Here's our agenda for the day. We're going to be going through our house of quality, we're going to go through our final design, design alternatives, and the evaluation matrix we use to determine our final design. Next, we'll show a short video of the robot in competition. We'll show a final bill of materials for our robot. And then we'll go into some team dynamics, conclusions, and insights, and we'll finally give some recognition for the class. So as you can see in this house of quality, we really want to focus on three key customer requirements. High scoring, autonomous, and safety were the three customer requirements we deemed to be the most important for our team. Now, as you know, these are all stated in the problem statement, but we chose to focus on these when we designed our final design. So here's our final design. We named it Blow in a Fuse because, as Etazaz knows, we have blown multiple fuses with this design. As you see with this system, we have the tennis ball arms that we've used throughout the competitions. They are activated by an actuator in the middle that pushes out and pushes both arms, and egress is pulling the arms by a string through the middle of them. The other actuator is used to push the solenoid ping pong ball mechanism out to the middle of the track. The solenoids fire through the switch in the front, and once the switch is hit once, one solenoid fires, which is the first one. And then once it's hit a second time, the second one in the back fires, depositing two ping pong balls in each red zone. As the ping pong ball mechanism egresses through the motor in the back, the dogbone system pulls the dogbone back into our robot, so we do not have the negative 13 on our score due to the dogbone. Now I'll pass it off to Siper to talk about our design alternatives.
Thanks, Robert. So this is design alternative 1. Its name is Demolition Derby. The way this one pushes the dogbone out of the home zone is with a rolling cart. This rolling cart, it's held in place by a solenoid, and the solenoid activates, releasing the cart, and the cart pushes the dogbone out of the home zone. To get the tennis ball, this design has two drawer arms attached to an actuator. The actuator fires out, and with this force pushing the drawer arms over the tennis balls, attached to this actuator is a string that once the actuator goes back in, the string pulls in the arm, thus the tennis balls. To get to the center, this design uses drawer arms attached to a swinging arm. The swinging arm rotates out with a motor, and then the drawer arms extend out with a motor as well to the center. To get the doll, this design uses a doll grabber attached to an actuator. Once it reaches the center, the actuator fires, grabbing the doll and pulls it back in. To release the ping pong balls, this design uses a solenoid type mechanism that once it's in the correct home zone, the solenoid pulls the door open and the ping pong balls are released. This is design alternative 2. Its name is Wacky Inflatable Arm Guy. The way this design gets the dogbone out of the home zone is it uses a sweeping front arm that pushes the dogbone into another person's home zone. To get the tennis balls, this design uses a double hinged arm attached to a string which is attached to an actuator. These actuators are flushed with the arms, and once they push out, the front arms go out over the tennis balls. Once it goes in, the string retracts these arms back in, and thus retracting the tennis balls. To get to the center, this design uses a 3-hinged arm. Once it gets to the center, the PVC pipe in the middle of the second arm shoots into the rotating centerpiece, and the zone that it shoots into, red zone or blue, that's more up to chance. So this design isn't as good in that, but it gets the ping pong balls all into a zone. To get the doll, it uses a rake that goes over. This rake is on the third arm, and then it pulls the doll back into our zone. This is design alternative 3. Its name is the Flying J. The way this design pushes the dogbone out of the home zone is it uses a double hinged arm with a wheel at the end. Once this arm is released, it pushes the dogbone into the egress zone out of the home zone. To grab the tennis balls, this design has two arms flush with an actuator. Attaching these two is a string, so once the actuator fires, it fires the arm over the tennis balls and pulls back in with the string the tennis balls into our home zone, similar to design 2. To get to the center, this design uses a motor attached to drawer arms. It extends these drawer arms out to the center, and at the end is a doll grabber to grab Morpheus once the IR sensor tells it to. To release the ping pong balls, this design uses a door dispenser attached to a motor and a switch as the input. The final design alternative is named Ping Pong Sensei. The way this design pushes the dog bone out is similar to the previous design. It has a double hinged arm with a wheel at the end that pushes the dog bone into the egress zone. To fully egress, it uses a pulley system with strings attached to the end. To get the tennis balls, this design uses a drawer arm that is pushed out with an actuator over the tennis balls and then retracted in with a string attached to it. To get to the center, this design uses a sweeping arm that goes out as far as it can, and then the rest is up to the drawer slide that goes out fully to the center. Before it reaches the center, right at the red and blue zones, there is a ping pong ball dispenser that releases the ping pong balls in the red zone, and at the end of this extender is a scooper that grabs Morpheus when the IR sensor tells it to.
Thanks, Abir. So here we see how Design 1 compares with all the alternatives. Namely, that it has the highest relative total of 0.79, which is 0.07 higher than the next design, which is Design 5 Ping Pong Sensei. Here we see how Design 1 compares to all the other designs in regards to the most important customer requirements. Out of all the alternatives, Design 1 does better in high scoring and ease of setup, and it distinguishes itself by consistently scoring higher in the most important customer requirements than all the other design alternatives. Here you see the bill of materials. It shows that the total cost to produce Design 1 was $92.50, where the most costly item were the drawer sliders, and the least costly items. The least costly item was the 1 inch by 2 inch by 10-foot piece of wood for the tennis ball arms. Now we'll show you a video of our robot performing in the competition.
Alright, ready in 5, 4, 3, 2, 1.
So I hope all of you enjoyed the video, and I'll be closing with a few final thoughts that our team had on some things. And first would be our team dynamics. We wanted to comment on a few things here. So for our schedule, it turned out that it worked really well for us to work Saturday to Wednesday and write reports and build the robot for the week during this time, and then sort of use Thursday and Friday as rest days. So for our team style, we just want to comment on this as well. We were more laid back, but when work needed to be completed, everyone was focused and everyone put their heads together to accomplish the goal that needed to be completed. As far as competition teamwork for us, it really improved as compared to previous times in this semester. Boxing and setup time took way less time than it had previously. We averaged about a minute to box in the final competition, and that's more than a minute savings from the qualifying rounds. And here we have some conclusions and insights on the project as a whole. So our robot qualified 31st into the final competition. We completed 2 rounds and moved on to the single elimination rounds in the competition, and we ended up finishing for a tie for 34th. So the tennis ball mechanism performed as expected, and that was the thing that we knew was going to be consistent for our machine. And we think it could have been improved by increasing the speed of the arms, and we think this is what allowed us to move on in the competition as far as we did. So as far as what we could change, we think we would probably change the tolerances for our machine to be able to work on different tracks, because the tracks were variant, and I think we were a little too precise and we needed to allow for more room there. Also, if we were given more time, we would probably focus on more test trials. Just more testing is always good, and probably more predetermined plans of construction, so that we would spend less time building it. And to wrap it up, we wanted to say thank you to our professors and our TA. Thank you, Edizaz, for spending all the time that you did in studio and out of studio helping us all out. Dr. Saldana, thanks for your time. Thanks for your time in studio, and thanks for going in or reading over all of our reports and giving us great feedback on that. And we'd also like to thank Dr. Urbina for visiting and learning more about our great university. Thank you.